Okay, next presentation is TCP and Automotive Ethernet, how to resolve the everlasting struggle. I would like to welcome Karl Budweiser from BMW and Iago Alvarez from Technica Engineering. I give you the floor.
Thank you for the kind introduction. I will try to use that microphone and place myself on the right side, on the right-hand side, so that light doesn't have to travel that far to the left of the audience. Let's see how this works. Okay. Sorry. Our talk is about TCP and Automotive Ethernet. And unlike for the internet, for TCP in road vehicles, both reliability and performance are of fundamental importance, as we do not only have to avoid systematic failures, but also sporadic errors. This presentation is circling around the questions: how can we deal with the implications of off-the-shelf TCP IP stacks, especially the embedded ones, and basically how to achieve both reliability and performance for upcoming and future automotive use cases. To start off, I will give a brief recap about the TCP protocol. Then I will, or actually we will, have a closer look at the programming process, as well as the problems that we were faced with during system development. To this end, I will try to walk you through a trace and discuss some of the main effects of embedded TCP IP stacks that we saw. Next, Iago will present actually the proof of concept setup that we use to, first of all, reproduce these effects, and second, to prototype the different performance measures that we investigated. Afterwards, we will discuss the results by putting the different performance measures into perspective. And last but not least, we will give hands-on guidelines how to configure your TCP IP stack and actually achieve highest performance within road vehicles. TCP is actually a transport protocol. It's where sender and receiver establishes a state to exchange data bidirectionally. The main goal is to stream data from one buffer into another, because TCP provides both segmentation as well as reliable in-order delivery of packets without duplications or loss. It is perfectly suited for that goal. With pipelining, TCP can even increase throughput because it allows for sending more than one packet at a time. However, to prevent the sending TCP from overwhelming either the network or the receiver, you need additional measures. These two measures are known as flow control as well as congestion control. We will have a deeper look at both measures on the next slide. First of all, the sending TCP knows a number of packets which are already acknowledged. It knows a number of packets for which acknowledgements are outstanding, they're missing, not yet acknowledged. It knows a window of packets which are allowed to be transmitted, and it knows packets which cannot be transmitted because, well, they're not yet in the sending window. Now, pipelining does nothing else but limit the sending window. That is, it allows for, flow control does nothing else but limit the sending window, meaning it does nothing else but allow for pipelining while protecting the receiver from too much information. Acknowledgements are generated by the receiving TCP according to the acknowledgement policy. This is actually an accept of the RFC that summarizes this policy. On the reception of an in-order segment, the receiving TCP is actually in the delayed acknowledgement state, meaning it is waiting another 500 milliseconds for another in-order segment. And if such another in-order segment is received, it is still in the delayed acknowledgement state. However, if it receives an out-of-order segment, which causes actually a gap in the data stream, the receiving TCP will react by sending a duplicate ACK, acknowledging the next expected segment, meaning the one that is still missing. Now, if there is a segment received that fills in that gap, that's our fourth option. The receiving TCP reacts by sending a cumulative acknowledgement immediately. TCP also knows some performance measures for reacting on acknowledgements. For example, if 3 acknowledgements are received, there is the option to start fast retransmit. That is, you send the oldest unacknowledged package again. Otherwise, if fast retransmit is not enabled or not provided, the retransmission would be bound to the expiration of the RTO timeout. Now, to avoid overloading the network, TCP knows congestion control algorithms, which actually take latency variations as well as timeouts or duplicate acknowledgements into account to fine-tune implicitly the sending window by updating the congestion window. The congestion window, so to say, provides borders in which the send window can be varied. In the slow start phase, actually we have for each and every acknowledgement that is received another MMS that can be transmitted. This results in an exponential increase until the threshold is reached. Now, when the threshold is reached, we are actually in the AIMD phase. That means for each and every round trip, we allow for sending another packet. And that is possible until until an incident is detected, and we do have different incidents, for example, a timeout due to packet loss or the reception of 3 duplicated acknowledgements. And now the exact congestion control algorithm defines what is happening next. I provided 2 different algorithms and options. There are plenty of those algorithms. For example, if you have 3 duplicate ACKs and you deploy the Reno algorithm, you reduce, well, of course, the threshold to its threshold half and start over with that value because actually the network is able to deliver, right? And basically that is how all these algorithms differentiate. Now, let's have a look at the programming. Maybe you know already our architecture. It's pretty famous with that surround view camera system. But that is not where the emphasis is today. Today the emphasis is on updating and programming the architecture. To that end, we have testers that can either be an external tester connected to the OBD port of the gateway, or it can be an OTA tester. We call this typically RSU. And this tester is nothing else but an external tester software, the software here, running on one of our vehicles. It's typically the head unit. Now, regular programming works as follows. We attach the tester to the OBD port, and thereby the activation pins are physically bridged. This information is provided as status OBD to signal all the Ethernet ECU the presence of an external tester. Now, the Ethernet ECUs have to react on that because they need to adapt to the external network. If they would not adapt, maybe there would not be any connectivity. And they do react by actually acquiring an external IP address so that you can have TCP IP connection. The gateway announces now these addresses of the Ethernet ECUs as well as itself to the external tester so that the tester can link the addresses with a vehicle. After changing the default diagnostic bus from external to actually direct programming, we can program and access the ECUs directly from the tester. That is something which would not be needed with DOIP, but in that architecture generation, we still use the predecessor, HSF-set. So with DOIP, you would not have to switch off the default diagnostic bus. Now, OTA programming is almost the same, and that is actually where our system gets stable. With OTA programming, we do nothing else but the OTA tester requests to pull up these activation pins to mimic that these activation pins are bridged, and therefore we call this logical activation. Yeah? And if that logical activation is up and running, if that signal is propagated properly, well, we are again in regular programming. Now, let's see what happens if you do that. I brought a trace, and I would like to do some trace analysis. In the very first, actually to start off, in the very first line, we see a segment from the head unit to the gateway with the sequence ID 60726 and the length 1460. As we have learned, TCP is always acknowledging the next expected segment, so let's add this up, and we get an acknowledgement from the gateway for the next expected segment being 62186. Now in line 3, what we see is that the head unit is actually sending the packet next 63646, meaning we're missing a packet, right? And that is a strong indication for a packet loss. As we have learned from the acknowledgement policy, the gateway is reacting on that with a duplicate acknowledgement, and we see that next. Now the gateway has something to transmit, so it is sending to the head unit some UDS messages, and it's still expecting the packet with the sequence number 62186. However, this is not counted as a duplicate acknowledgement. Yeah? Now the gateway it finds that the receive window is actually full, and it wants to acknowledge the reception of that packet, which happens in that line here. And of course, if the gateway is sending something, the receiving TCP on the gateway is again sending another duplicate acknowledgement. However, the retransmission does not happen before actually 200 milliseconds after the loss of the packet. That is, we don't have 3 duplicate acknowledgements, right? The gateway is not triggered by the head unit. So we can actually not send further data, and we have to wait for the retransmission. Now, when the retransmission happens, it gets really vicious. The gateway is now telling it's expecting the segment 6364, even we know it was transmitted before. Yeah, that means we have a vicious cycle. And that vicious cycle is caused to missing out of order support. So the gateway is not receiving that packet if it's not in order. So the general finding in the trace, we saw that we have pretty small receive windows, which prevent actually 3 duplicate acknowledgement. And not only that, they prevent an efficient bulk transfer. What else we have been seeing was basically that we saw lost segments all the time, those loss chains or retransmission chains due to missing out of order. And we saw that UDS messages were packetized even though that the Nagel algorithm was turned off, which is also a strong indication that we have timing variations and latency. Now, what were the implications of that? The implication that was we had flash abortions in 96% of all our flash updates, which is tremendous. Yeah? And the reason for that is that the UDS timeouts are way smaller than the RTO. Yeah? It's actually these 2 protocols do not interoperate properly. And we saw this basically in our 21 architecture, which is not really different from the 2018 architecture where we did not see that problem. The only difference is there are a couple of more ECUs, but this was not the problem, the main problem why this effect appeared. One of the problems was basically that the flash sequence was optimized for update via the gateway, because here you distribute, we start by flashing the gateway and then flash all the ECUs behind, and we distribute pretty evenly, right? With OTA tester, we always have to go to the gateway, so a bottleneck is here. We have a bottleneck here, and that bottleneck gets even worse because we do have inside a speed rate mix. There is the head unit system on chip, which has a gigabit interface to the switch and a 100 megabit interface from the switch to the gateway. And now with that mixed speed rate, the problems arise. We had that mixed speak rate also in Service Pack 21. However, we had less performant hardware, meaning that our OTA tester in 2018 have had less traffic offer, so this bottleneck was not, did not appear. In addition, we had an implicit traffic shaping. Maybe you've heard Don's presentation on that, what this can reach, traffic shaping. The implicit traffic shaping happened because we had pretty small received windows on all these ECUs, right? And that means you cannot send too much data at a time, and the summation of the data did never violate the available bandwidth on the link to the gateway. Yeah? We were not aware of that. Okay? That means now if you have minor shortcomings in the configuration of your TCP stack and little changes, you might have severe consequences. And believe me, it's unbelievably hard to really debug something like that. With that, I would like to give over to Iago to see how to configure the TCP IP stack so that you will never run into problems. Thank you.
Okay, well, first of all, thanks a lot, Karl, for introducing this topic to us. And now we'll take over the second part of the presentation, and we'll speak about the different ways that we have to optimize the TCP protocol for automotive applications. So, in order to discover how this works, we have designed a proof of concept setup to simulate both ends of the TCP communication. On one side, the sender, and on the other side, the receiver. This proof of concept setup consists on two Linux-based systems communicating to each other, and it will allow us to cover some technical needs for our experimental procedure. First of all, we will have control over several TCP parameters and features, like round-trip timeout, auto-forward support, the fast retransmissions mode, and so on. And most importantly, it will allow us also to create some fault injection scenarios where we could actually delay segments that are in transit, simulate a receiver that does not support the reception of auto-forward segments, and even drop segments that are in transit. Dropping segments here is probably the key feature that will always be activated, because our main goal here is to evaluate the TCP performance under these circumstances when we have TCP loss segments. So now let's speak about the different experimental procedures that we performed and the results that we observed. Our main goal here is to find out which are the TCP problems that have a bigger impact in embedded stacks, and which are the parameters that affect those problems. And having this into mind, we identified two critical issues that Karl already suggested before, which are the retransmission chains due to a missing auto-forward support on the receiver side, and also an overall poor recovery and performance after segment losses. In this slide, we present two mechanisms to improve this. So first of all, auto-forward support, and second of all, the reduction of the minimum retransmission timeout on the sender. So for this test, we started from a baseline scenario, a reference scenario, where we do not support auto-forwarder and where we have a high value for the minimum RTO of 200 milliseconds. Why are we using this big value, this 200 milliseconds? Because this is a standard value used for the internet, for traditional networks, and also a common standard for Linux. We observe in the two different scenarios working separately that we have, in both cases, better results in terms of throughput. And what's also very important to say is that both optimizations combined show even better results when they're working together, like we can see in the last picture. So let's talk about these two scenarios separately, more in detail. We have seen that auto-forwarder helps us, but how exactly does this work? In this slide, we can compare the reference scenario on the left side, the reference scenario on the left side and the improved scenario. In the first case, whenever a segment is lost, all the segments that are sent afterwards are dropped by the receiver because they are received out of order. And therefore, they also need to be retransmitted by the sender. This creates a chain effect that is not stopped until all retransmissions are through. So the one of the original loss plus all the other packets that were dropped by the receiver. This, of course, does not happen in our improved scenario. In this case, the receiver can acknowledge the segments that are sent after this loss. Therefore, the sender only needs to retransmit whatever has been lost and nothing more. Also, selective acknowledgement is another feature that we will explain later, which can give us additional advantages in the case that out of order is supported. We have also seen that by reducing the RTO, we have better results. But what exactly is this value? The RTO is a time that passes between the transmission of a segment until its retransmission, in the case that we never receive an acknowledgement message for it. This is a value that is always been dynamically calculated and has a limit lower value used by the stack, which is the RTO min, and this value must always be larger than the round trip time. Otherwise, we will not give enough time for the sender to receive the acknowledgement, and therefore we could have unnecessary retransmissions. Having this in mind, that we need to keep this value always larger than the round trip time, we can substantially reduce this value from the typical 200 milliseconds to be more adequate for automotive network properties, where we have lower latencies. We also discussed SAC a few minutes ago, and with selective acknowledgement, what a receiver does, it can identify more than one hole or gap caused by a segment loss within one acknowledgement message. So that means also that the sender can retransmit more than one hole or gap in one round trip time, and thus we improve a lot latency and speed recovery. The effect that selective acknowledgement has is not as big as the one that we obtain with out of order or with, by reducing the RTO, but it can help us in terms of recovery speed time and to smooth out data after these segment losses. So fast retransmissions and recovery mode is another key feature that is really interesting, and when entering this mode, the TCP sender assumes that a segment has been lost whenever it receives a third duplicate acknowledgement message. If this happens, the sender retransmits the segment immediately without the need to wait for the RTO to expire. In order for this mode to work, we need to make sure that applications keep sending data. Otherwise, if data is not being sent, we will never receive a third duplicate ACK, and we will not be able to detect this segment loss as fast as we could. Why is fast retransmissions so interesting for us, for automotive networks? This is because by nature, automotive networks are local networks, and reordering is not to be expected. So there is no need to wait for a third duplicate ACK to distinguish between a segment that has been lost and a segment that might have been delayed, because it's probably been lost. So we basically, with the use of our proof of concept setup, we have experimentally proved and seen that we can trigger fast retransmissions after a second and even a first duplicate ACK. Because the goal here is to react as fast as we can upon this loss. So in contrast with all of these features that have a big impact on stacks, we have also observed some other minor parameters, other features that have a lower impact. A good example is the effect of different congestion control algorithms that we have tested. That, as we can see here in this picture, we have seen minor differences between them. So it's not really, they don't really have a big effect when it comes to an improvement in TCP performance for our use cases. Also, none of these algorithms can deal with one of the main issues here that Karl suggested, which is the retransmission chains. So, having taken a look at all of these features, all of these things that improve our TCP stack, we can state an overall recommendation. First of all, we have to keep in mind that the retransmission timeout must always be kept larger than the round-trip time of TCP, but we can drastically reduce this value to meet our needs, to meet the needs of the automotive networks. And we recommend to set up this value to 3 or 5 times the typical main cycle for TCP. Then second, out-of-order reception should be supported on the receiver side in order to avoid having these unnecessary retransmissions and lost chains. Also, we have seen that selective acknowledgement can give us additional advantages in the case that out-of-order is supported. And fast retransmissions is also a very interesting topic, a very interesting feature in the case that we have large application messages. We have also seen that in order for this to work, besides having really big or big application messages, also the window size, the TCP window size must be large enough to support this, to make sure that we can receive duplicate acts in transmission. And last but not least, that congestion control has never been optimized for automotive applications, and this is an urge, this is a need that we have now, especially because we have no reordering, and therefore there is usually not a need for 3 duplicate acts in order to trigger the fast retransmissions mode. And to finish the presentation, I'd like to give a brief summary and some outlook points. So I think the key message of this presentation is that even though TCP is an old and well-known protocol, it has never yet been optimized for automotive applications. And we should dedicate it, we should master this protocol before we start implementing and discovering new technologies on top of it. We have seen that embedded stacks without out-of-order result in lost chains, in retransmission chains that can be critical. We have also seen that the 2 optimization techniques that have a bigger impact is on one side RTO tuning, the RTO min tuning, to improve the reaction time for retransmissions, and also the out-of-order support to avoid having such lost chains. And as outlook points, well, we can highlight the following. We strongly recommend implementing advanced traffic shaping techniques in order to avoid segment losses in the first place due to congestion in the switches. Also, that we need to customize congestion control algorithms to meet the automotive network properties. And also, it's ongoing the investigation of the use of application keep alives, like, for example, the SumIP magic cookie, after application data to make sure that we always keep sending data, that the applications keep sending data, and we can always trigger fast retransmissions to have a faster reaction time. And this is the end of the presentation. Thanks for your attention, and now we will gladly respond to any of your questions. And I also have written here our contact information for any issue you might want to address to us. Thank you.
Thank you for your presentation. Sorry, it's behind the schedule, so 1 or 2 questions. Any questions?
Hi, I'm Rajiv Roy from NXP. If you have CB in a network, you can have out-of-order. So RTO makes sense, but I did not quite understand how you would deal with out-of-order acts.
I'm sorry, can you repeat the question? I didn't really understand. You said there. Sorry.
If you have redundancy CB, you can have out-of-order packets. And then how would you deal with these? So RTO reduction makes, I understand, but then how would you handle the acknowledgement part in that kind of situation?
I mean, you mean for replication of the... Yeah, I mean...
Hello, Rajiv. Actually, BMW is not really keen on doing CB.
Yeah,
right?
no.
You might have read that stuff in the IEEE DG presentation that I gave on October the 12th. Now, if we had out of order, of course, this requires further fine-tuning. So you might either want to change your automotive specific, once we have an automotive specific congestion control algorithm, which now takes out of order again into consideration. So it depends largely if you want to have CB, then you have to react on out of order. Yeah. If you don't have that, you don't have to react on that, and you can get more out of your configuration. Okay.
Okay. Again, thank you for your presentations.